Okay, Larry is going to tell us about descending the space elevator. So we talked a while ago about the down problem, and he looked into how that might be done.
And I do not have a final answer, which you'll find out, but I'm going to augment a little bit of what Stephen was talking about yesterday about, and I'm looking forward to his talk later about energies for very large um, cargo. So last year, Stephen Griggs proposed to mine an asteroid and bring back metals over 20 years. And he talked about that yesterday a little bit. And he estimated the value of these metals. And I've been working on the space elevator for 20 years now. And for the last 20 years, there's been very little attention paid to going down. And Stephen brings up a business model that makes a ton of sense to bring material down. So now we have to solve the problem of how do you make it go down? Why use the space elevator to bring stuff down? Well, the first assumption is that stuff that starts out as asteroid material products ends up in geo after a long journey somewhere, excuse me, somewhere in the solar system. And then, as Stephen pointed out yesterday, the second assumption is that bringing hundreds of thousands of tons of material per year down is not feasible using aerobraked vehicles. And then climbers that have delivered their payloads to GEO are just waiting to be reused. The other thing is, if you think about the Earthport as a transportation hub, it becomes trivial to pick up cargo that's been returned from the asteroid belt from one place where it comes down. So I looked at what are the sizes of 5-ton chunks of material to bring down and what are their values. And I started with the LOX tank that I designed as a 5-ton payload. There would be two of them. So the 20-ton climber in my reference conceptual design is capable of carrying 10 tons. So there'd be two 5-ton LOX tanks, but each block that you see here is a cube of metal that also weighs 5 tons. And there's a person in the picture for scale. So you can see that any of these blocks of metal could be attached to a climber because they occupy less volume than the LOX that I already designed an attachment to the climber for. And Stephen talked a lot about platinum group metals, which are the most valuable metals. Rhodium is the most valuable of the platinum group metals and the second most valuable metal of all. And if you had two 5-ton blocks of rhodium, you would have a payload that's worth, at today's prices, almost $2 billion. So the other thing that you see by looking at this is it makes no sense to bring down the low value items. It doesn't make sense to bring down copper, iron, or aluminum. Those are much more valuable in space to build stuff in space. And I gave a talk in 2024 showing that the problem with building very large space structures is not the production of those materials on Earth, because we make about 1 billion tons of steel per year. We can't get it out of the gravity well at any kind of reasonable rate. Using the full up power of a mature space elevator system would still take about 53 years to build a Stanford torus in GEO. So this is problematic. So, but that's where asteroid mining and lunar mining comes in to fill the gap and provide us large quantities of lower value materials, but very high value in space. So what makes sense to bring back? I just talked about that. It makes sense to bring back the high value metals. Why would you do that? Because you need to bring something back to pay back the investors who have put over the money to pay for both the asteroid mining missions and the space habitat missions. So there's two methods of slowing a descender. You don't want a descender to turn into a meteor, okay? So you have to control its velocity all the way down. And if you look at the amount of power required to lift an ascender to GEO, that curve has to be followed backwards for a constant velocity descender operating at roughly 200 kilometers an hour all the way down. So you can let the regenerative brake, you can basically spin the motors that are already on the climber and allow them to generate electricity. And the issue is, what do you do with that electricity? So you have two choices for that. You have to offload it to avoid the descender from overheating, or you can resistively turn it into heat and just waste it by radiating it away. You need friction brakes in any regenerative system because at slow speeds, regenerative braking loses the ability to deliver the torque necessary to hold up the climber. But you can't use friction brakes the whole way down because you have to dissipate megawatts of power, and that would destroy the contact surfaces of the friction brakes. So they're the backup brakes at slow speeds and to halt the climber at the bottom. This is a typical uh, uh, block diagram for any regenerative braking system that shows if you want to power the motor, you go from the power source through the DC-AC inverter and into the motor. And when you're driving the motor by letting it roll down the tether, it puts power back through a DC-DC converter into what is shown in this picture as a high power density battery. But that's where the climber has to do something. There is no technology to store the total amount of power that the climber needs to get rid of. We've looked at SMEs, we've looked at all kinds of other options. There's no way to charge up a battery with all the power that the climber produces on its way down from geo. So you have to get rid of it. You have to take it somewhere. So one idea, and this idea is completely dependent on how heavy microwave transmitters are on climbers, is when you get to geo, the climber still needs the motors, the wheel compression mechanism, and the quick disconnect mechanism that holds the two halves of the climber together. But it doesn't need PV arrays, so you take those off at geo. Those are useful everywhere in space. And you replace them with microwave transmitters and rectennas, assuming that the power is going to be beamed to the ground and used. And the idea is if you do beam the power to the ground, great, you get some of the power back from the process of descending, but that's not the real point. The real point is to keep the climber from turning into a meteor. Most of the power to be dissipated happens low down on the tether when the power that you need to dissipate is high because gravity is high, and collecting the power from the descender is a bonus, but the critical element is getting it off. So this is what I did here is I just basically relabeled the PV arrays in my reference conceptual design of a climber, and you can see it has two gold blocks as payload, and I renamed the PV arrays to microwave phased arrays. There are lots of different ways of doing this, and it all depends on the mass of megawatt scale microwave transformers. And we don't know at the moment if that technology can be made light enough to be compatible with the mass budget of the climber. And that's the caveat. We don't know if megawatt scale transmitters can fit in the mass budget. And some of the estimates coming back from space-based solar power indicate that they might be too heavy for the climbers for the power required. This is the curve I was talking about, which basically is the amount of power going up. This is the amount of power you have to apply to a climber to allow it to escape the weight, the force of gravity. But going back, you probably have to dissipate more than this because of some losses. So this is a purely theoretical curve of the amount of power necessary to climb at 200 miles per hour and also to descend at 200 miles per hour, ignoring any losses. I have been working with an intern named Danush Salunke, who we've been trying to design graphene resistors that can get hot enough to take the power from the motors and radiate it away. And these resistors shown here have the right resistivity and the right area that they get up to 2,310 degrees Kelvin, and they dissipate 6 megawatts of power each. So it's hard to see, but at the bottom there's a strip of tungsten that is a weight for these things to keep them straight and flat. And the idea is that power comes from the bus that goes to the client that is coming from the climbers, goes in a circuit or through this resistor and heats up the resistor and the thermal radiation beams the power away. So right now, we don't have a fully vetted solution to the problem of power dissipation in the climbers, and we're looking at a number of options. And that's all I have.
Yeah.
Um, did you consider using air resistance as a way to substitute in for the friction braking as you get into the atmosphere?
No, I did not. Uh, you would so the whole issue of aero braking, um, air is basically just, I mean, sure, it works for something moving very fast because the force of drag is a function of the velocity squared. But the idea is you don't want this thing coming in hot in a velocity sense. So what is useful lower down in the atmosphere is, besides just thermal radiation from the hot surface, you also get convection down in the atmosphere, which we didn't look at how much that helps, but it does help some in getting rid of the heat from those sheets of graphene.
I was just thinking in terms of the total like cross section that we're talking about for rectennas and PV arrays, that should definitely like make a difference in the terminal velocity as you get closer to the bottom. So I was just thinking if there was any dual purpose there.
You saw some of the pictures yesterday in Avery's talk about how large rectennas get. And that's an issue I have a serious issue with some of those sizes. Peter's asking if we could use the power to heat the tether itself, but only well above the climber to avoid heating the climber. I don't know how to do that. Certainly the tether is capable of taking high temperature. How you get the power into it is not clear to me if you're trying to do it in a way that's not near the climber. And then how close would an upbound climber need to be to transfer the power via a thin wire electrical connection, assuming two tethers in parallel? Doug, are you saying that there would be a wire actually going from one climber to the other? Because that sounds really hard to coordinate.
Yeah, I guess I'm thinking of the way high building elevators work that have a cable looped over a pulley. Uh, in space, you wouldn't necessarily need a pulley because you're attaching to the climber, but is there any way to make an electrical connection to a climber that is maybe 500 kilometers below or something like that?
Actually, Avery has done calculations on microwave beaming from one climber to another. And the conclusion that he reached before, and Avery, correct me if I say anything wrong, is that they have to be within like 100 kilometers for it to
Oh,
be work. And because the tether is so long, that means hundreds of climbers on the tether, which is a challenge to the weight of the tether.
okay.
They're too close together, basically, if you have that many climbers.
Yep.
That wasn't for microwave. That was for conduction, Larry.
Oh, okay. I misremembered that. So that's how close they have to be if you're using the tether as an electrical conductor.
I think that using microwave power beaming between climbers would be similar.
Okay,
In
so
order to keep the arrays, transmit and receive arrays at a reasonable diameter, it would be similar.
so that means you'd still have hundreds of climbers on the tether at one time.
Yeah, it's a big pipeline. Every 100 kilometers or so, you'd have a climber, and you'd still have to have a mechanism for them to pass each other.